Okay, Chapter 5, Section 2, Integration by Substitution. So in this section, we're going to continue to further our development of integrals, and we're going to develop this technique called integration by substitution, and it revolves around the chain rule. So let's take a minute to refresh our memories about the chain rule back from Chapter 3. Okay, so if you recall back from Chapter 3, this was our chain rule. So if we want to take the derivative of a composition of functions, f composed with g, then the chain rule tells us that what we can do is the derivative is equal to the derivative of f evaluated at g times the derivative of the g function, right? So the answer to this composition function, the derivative of a composition of functions, is formed by taking the derivative of the exterior function, f in this case, and then evaluating it at g of x, then multiplying it by the derivative of the interior function, g of x. So as a quick little example, just to refresh our memories on the chain rule, one type of question could be this one. Find the derivative with respect to x of, and then maybe we could have 2x to the third power plus 5x, and all of that raised to the power of 7. Okay, so the derivative is going to be equal to the outside function. Now the outside function, just the way I've written it here, we can think of the outside function as f of x equals to x to the power of 7, right? Blank to the power of 7. Whereas the inside function, the g, is the 2x to the power of 3 plus 5x, right? So then we can think of this as a composition of functions. It's the f function evaluated at g, right? So here, I'll write this down. So then if this is how we define the f function and the g function, then f evaluated at g of x is equal to exactly that. Is equal to 2x to the third power plus 5x, all of that raised to the power of 7. Okay, so this is a composition of functions. The outside function is this f1, x to the 7th power. The inside function is this 2x to the third plus 5x. So if I want to take the derivative of this composition of functions according to the chain rule, I'm going to take the derivative of the outside function, which is just going to be equal to 7 blank to the power of 6, right? So if this was just a single variable like here, it would be 7x to the power of 6, but we do have a more complicated statement, so we just copy that right in here, plus 5x, times, and now we want to take the derivative of the inside part, which would then be 6x to the power of 2 plus 5. Okay, so that would be our derivative. One more quick example. How about if we want to take the derivative with respect to x of, say, e to the power of 2x to the third power plus 2x squared. Okay, so again, the outside function, f of x, is just e to the x, whereas this inside function is the 2x to the third power plus 2x squared. And again, we can see how if we want to evaluate these two, we can think of this as f evaluated at g of x is equal to exactly that, is equal to e to the power of g of x, and that is e to the power of 2x to the third plus 2x squared. Okay, so we can think of this as a composition of functions. So the chain rule will apply. Chain rule says take the derivative of the outside function, e to the x, well, the derivative is e to the x. So we would just copy this, e to the 2x to the third power plus 2x squared, times the derivative of the g function, which is going to be times the derivative with respect to x of 2x to the third power plus 2x squared, which then becomes e to the 2x to the third power plus 2x squared times, and then this becomes 6x squared plus 4x, like that. Okay, so taking derivatives, using the chain rule, not too bad. So let's come back over here to the general form of our chain rule. Now let's think about this. Let's say that I have my derivative with respect to x of f evaluated at g of x. And then on the other side of the equal sign, I have the f prime evaluated at g of x times g prime of x. Erase this. Okay, so now let's say that I take the integral of this side, dx, and the integral of this side, dx. Okay, now this, I mean, I don't know what this is, but this should be really easy. Remember that taking integral, taking a derivative, they're inverse operations of each other. These things undo each other. So on the left-hand side, this is just going to be f of g of x equals this integral of g of x times g prime of x dx. Except remember, there's a whole family of functions that could satisfy this condition. So we have to consider adding a plus a c. Okay, and that is the basis of what we're going to do in this section. This gives us a way of integrating really complicated things that take this form. Okay, so that's really what we're going to do. If we run into something that happens to fit this form, then we know that we can integrate it and it equals to that. That sounds kind of complicated, but okay, let's go back to the two chain rule examples we just visited over here. So let me erase this right here. We established that if we have this function, then this is its derivative. So what this is saying is that if we happen to be asked this, find the integral of 7 2x to the third power plus 5x to the power of 6 times 6x squared plus 5 dx. If this is the question, easy. This comes from that. So the answer is just going to be 2x to the third power plus 5x to the power of 7 plus some constant, right? And likewise over here, let me erase this thing, I don't need this anymore. So likewise, we established that if we were given this composition of functions, we find its derivative, here is the derivative. So this is saying that, okay, well, if, on the other hand, you're asked to find the integral of e to the 2x to the power of 3 plus 2x squared times 6x squared plus 4x dx, find that integral, and like, okay, well, here it is. It's that. So the answer is e to the 2x to the power of 3 plus 2x squared, but recognizing that the answer is going to be something whose derivative is equal to this, right? And we found it. Here it is. It's this one. But also, I could just add an extra number here, like say 3, because the derivative of this, well, when I take the derivative of 3, it's going to be 0. So I can always have a constant at the end. So don't forget that constant. Plus some constant. And there you go. It's easy. Good. So we're going to be dealing with integrals that are the result of taking the derivative of a composition of functions. Okay, so solving these integrals is both super easy and at the same time super hard. Um, it's really just about pattern recognition. There really isn't much work that we do except to recognize that we are staring at the output, the derivative of a composition of functions. And that in itself can be hard. So we have to learn some general patterns that can kind of guide us through the path. Uh, but it can be hard to find that pattern. But once you find that pattern, then it's super easy, right? So it's kind of a weird thing. It's easy if you know what you're doing, I guess. If you recognize it, if you see the pattern, then it's easy. Otherwise, they can get kind of ugly. So let's look at some patterns. So in general, if we have something that looks like this, let's say we have some function f of x raised to the power of n, and we also have f prime of x, and then this is dx, and then we want to find this integral. Finding the integral of some function raised to the nth power times, and it just so happens that the derivative of the f function is right there, then here the pattern is going to be to think about the power rule for this one. So this is going to be equal to f of x raised to the power of n plus 1, right? So thinking about the derivative of this, we bring down the n plus 1, subtract 1, that would give us the n. And so we have to adjust by putting an n plus 1 out in front. And then we must consider a constant plus some constant. So, for example, the integral of 3x squared plus 2 raised to the power of 8 times 6x dx. Okay, so when you're faced with this question, you have to recognize that this 6x is the derivative of this function. So we can think of this as some function raised to the 8th power, and its derivative is right out here. So following this pattern, I can see that the answer is going to be 3x squared plus 2 raised to the power of 8 plus 1, which is going to be 9. And then we have to adjust for that constant by also dividing by 8 plus 1. And then there's a constant at the end there. So this is power of 9. Let's rewrite this as 1 over 9 times 3x squared plus 2 raised to the power of 9 plus some constant. Okay, let's check it. If it works, if it's true, it must be the case that the derivative of this equals to that. So the derivative with respect to x of 1/9 3x squared plus 2 raised to the 9th power plus some constant. Okay, so using the chain rule, we bring down the 9. That's going to be equal to 1/9 times 9, 3x squared plus 2 raised to the 8th power times the derivative of the inside function, which gives us the 6x. Good, so now these 9's cancel, cancel, and we have exactly what we expected. This equals to 3x squared plus 2 raised to the power of 8 times 6x. Good. Okay, so you might be wondering, well, what if that 6x isn't there? Let's say that you're just given this one, 3x squared plus 2 to the power of 8 dx. You would think that this one's easier because it's less complicated, perhaps, but you would be wrong. We need that 6x to be there. It complicates life if it's not there. It's convenient for it to be there because it is the derivative of this inside part. So the exercises you'll face in your homework are very, very carefully cultivated to work out nicely. Now, there are some nice little tricks and twists that we'll deal with, but by and large, only certain types of questions will fit this pattern and will be solved by this method. Okay, so they have to provide you the right question and the right value there. If it's not there, then in some cases there's a way to solve it. There's a way to tweak it and figure out the answer. In some cases, we might have to apply a different idea, a different property to figure out the integral. And in some cases, we might not be able to find the integral. Not every integral has an answer, at least not an answer that we can do or get an exact answer for. We can do like approximations and all kinds of other stuff, but all of that is outside the scope of our class. For us, right now, just know that all the questions we have will be very carefully selected, right? The author has gone through a lot of trouble to very carefully give you questions that will work out nicely. Okay, so that's one of our patterns. Let's look at another pattern. So another pattern that we're going to be interested in is that if we have e to the power of f of x, and we also happen to have that f prime of x multiplied right next to it, and we're trying to find the integral of this, then the answer is just going to be equal to e to the power of f of x plus a constant. Okay. So for example, let's say you're asked to integrate e to the power of x cubed times 3x squared dx, right? So your eyes quickly go right here and go, okay, look, this is the derivative of that. How convenient, right? The derivative of that. So according to this pattern, then this says that the answer is just going to be e to the power of x cubed plus a constant. Right, let's check it. Is it true? Right, you can always find or check your answer by taking the derivative of the answer here, and if it works, it should give you the integrand. Okay, so the derivative with respect to x of e to the x to the third power plus c, well, the c is not going to have any impact. That's going to be plus 0 at the end there. And the derivative of e to the x cubed times the derivative of the function in the exponent, which is going to be times the derivative with respect to x of x to the third power, which then results in exactly what we expected. This becomes 3x squared, and that's the result here. Okay, so another easy, straightforward pattern. And finally, let's take a look at this pattern. Okay, so finally, what if we had 1 over f of x times, and again, very conveniently, we have the derivative of f of x right next to it, and we're trying to find this integral, dx. Then this is going to be equal to ln of absolute value of f of x. Remember that the derivative of ln of x is equal to 1 over x. So that's going to give you this part of it, times the derivative of the inside function, which is that, plus some constant. Good. So again, for example, if we had the integral of 1 over 3x squared plus 2 times 6x dx, if this was what you were being asked to integrate, then following this pattern, we see that this would be equal to the ln absolute value of 3x squared plus 2 absolute value plus some constant. And if we take the derivative and check, derivative with respect to x of ln absolute value 3x squared plus 2 plus a constant, you can see that this is equal to 1 over 3x squared plus 2 times the derivative of the inside part times d dx of 3x squared plus 2 times the plus the derivative of c, which is 0, and the derivative of this guy is going to be equal to 6x. Oh, which is that? So it's exactly what we expected. The answer is going to be equal to 1 over 3x squared plus 2 times 6x. Right, the integrand from over here. So also notice that when we find the integral, we have to introduce these absolute values because the argument of the ln function has to be positive. We have to guarantee that it's a positive number. But once we analyze the function that's inside here, if we can be satisfied that it's always going to be positive, then we can go ahead and get rid of the absolute values. So if you're wondering why sometimes you run into the absolute values and sometimes you don't, that's because in some cases they're no longer needed. I know that no matter what input value x is, positive or negative, it doesn't matter, x squared is going to be greater than, equal to or greater than 0. Right? It's a positive answer, or it could be 0. Even if it's 0, then we get 3 times 0, that's going to be 0, plus 2. So the output, the range of this function is always strictly greater than 0. So the absolute values are not necessary in this case. So this becomes ln of parentheses 3x squared plus 2, just because the absolute values are redundant in this case. Okay, so we have 3 general properties that can help us figure out integrals. Okay, so here are the 3 patterns we just looked at in a nice pretty box provided by your author. So this forms some patterns of some general integrals that we might run into. Okay, so let's use these to solve a few questions. For example, let's say we have this. Find the indefinite integral of the following. The integral of x to the power of 5 minus 2, parentheses cubed, times 5x to the power of 4. Okay, so notice that, or I should quickly notice that if we think of this as the inside function, then the f, then f prime, the derivative, is right outside here. Right? The derivative of this is that. Right, so put note. If f of x is equal to x to the 5th power minus 2, then f prime of x is equal to 5x to the power of 4. Okay, so its derivative is right out here. So this is the one that's the integral of f of x to the power of 3 times f prime of x dx. That's what we're staring at. And so the pattern tells me that the answer is going to be the integral of x to the 5th minus 2 to the power of 3 times 5x to the power of 4 dx is equal to x to the power of 5 minus 2 raised to the power of 4, and then there's a 1 over 4 out here, plus a constant. Good. And we can check it. Bring down the 4, cancels with a 1/4, subtract 1 from the exponent. We'll have this to the power of 3 times the inside function, which will be exactly that. Good. So let's check it. Check the derivative with respect to x of 1/4 x to the 5th minus 2 raised to the power of 4 plus a constant c. This is exactly equal to 1/4 times 4 x to the 5th power minus 2 to the power of 3 times the derivative of the inside function, thanks to the chain rule, which gives you x to the 5th minus 2. Good. So the 4 and the 1/4 cancel. And so I end up with exactly what I had expected. X to the 5th power minus 2 raised to the 3rd power times 5x to the power of 4. Right? So that's exactly the integrand over here. Good. So this confirms that this is our answer. Okay, so the hard part is just recognizing the pattern, identifying that this is what's going on, that if we think of it as an f of x raised to the power of 3, that the derivative of f of x is right there, standing right next to it there, be multiplied right next to it. And if it wasn't there, then life would be more complicated, right? And we need it to be exactly its derivative. To some degree. We'll be able to manipulate it a little bit, as we'll see in a few examples down the road, but for the most part, it needs to be there. If it's something else, it gets more complicated, or we may not be able to solve it. Okay, let's try another one. How about this one? Okay, so e to the power of x to the third power, and well, in fact, its derivative is right next to it. Okay, so again, here, if we see f of x is equal to x to the third power, its derivative, f prime of x, is equal to 3x squared. So the integral of e to the x cubed times 3x squared dx is in fact equal to exactly e to the x cubed plus some constant. Good. I think I had already done one like this anyway, so let's move on. Good. So if you take the derivative of this, you're going to get exactly that. Okay. What about this one? Again, if you notice that the derivative of this denominator is equal to 4x to the third power, then if we think about f of x equaling just the denominator, 1 plus x to the fourth power, then its derivative is equal to 4x to the third power, which is right there. So the integral in question is really 1 over f of x times f prime of x. That's the general form that we have, where f of x is equal to that. Right? This is the integral in question, 1 over 1 plus x to the fourth times 4x to the third power dx. And so we see from our pattern that this is equal to ln of absolute value of 1 plus x to the fourth power, absolute value, plus some constant. Again, we have a situation where this can't possibly be negative. Any number raised to the power of 4 is going to be positive or 0. Plus 1, definitely going to be positive. So the absolute values are no longer needed, and this is just parentheses 1 plus x to the fourth power plus some constant. Good. Again, we can check it. Check. The derivative with respect to x of ln of 1 plus x to the fourth is equal to 1 over 1 plus x to the fourth times the derivative of the inside function, which is going to be derivative with respect to x of 1 plus x to the fourth. And that gives you exactly what we expected. Gives you exactly 1 over x, 1 plus x to the fourth times 4x to the third power, right? Exactly the integrand from over here. So we found it. We found a function such that its derivative equals to that. Okay, so if you're asked to integrate something and it fits the formulas exactly as we've seen in these previous examples, using formulas 1, 2, and 3 from above, then integrating is super easy. You just have to identify that the pattern is right there and then just apply it, right? No real work needs to be shown if you can identify it, if you can recognize it, and if that's in fact exactly what they've given you. However, it won't always be that easy. Sometimes it's hard to identify the pattern, and sometimes the pattern is not quite there. It's just off by just a little bit, and we'll have to do a little bit of tweaking to make it fit the pattern and be able to integrate it. So in the more complicated cases, we're going to develop this idea of a substitution method, the method of substitution. Okay? So a definition. If y equals to f of x defines a differentiable function, then the differential dx of the independent variable x is an arbitrary real number. And the differential dy of the dependent variable y is defined as the product of f prime of x and dx. So dy equals to f prime of x dx. we can think of it this way. Let's say we had y equals to some function f of x, and we want to take the derivative with respect to x on both sides. So d dx of the y and d dx of the f of x. Good. All right, well, this is just dy dx, which equals to this, and assuming that f of x is differentiable, well, we can just write it this way. Good. Okay, well, what this is saying is that we want to think about this as something we can separate. Dx represents some arbitrary number, so what we can do is think about multiplying both sides of the equal sign by the dx. So we're going to multiply this side by dx. We're going to multiply this side by dx. On the left-hand side, these kind of cancel each other out. And so we're able to solve for the dy. The dy equals f prime of x dx, right? That's what this is saying right here. Okay, how is all of this useful? Let's just jump into an example. Okay, so let's say we're asked to integrate this this function. So we have x squared plus 2x plus 5 raised to the power of 7 times 2x plus 2 dx. Okay, so you can probably already recognize that this function, if we think of this function as an f of x, then this is its derivative, right? So the derivative of this is this. So this fits one of our patterns from before. We don't have to use substitution to solve this one. But let's use it here while we already know the answer. In fact, let me just write down what that answer is going to be. Just based on recognition of patterns from before, this is pattern 1. This is some function f of x raised to the power of 7 times f prime of x, and we're trying to integrate that, right? This is the pattern that we have here. So we know that the answer is just going to be x to the power of 2 plus 2x plus 5 raised to the power of 8, and then we have to adjust for that constant by multiplying it by 1/8. Right? The 8 is achieved by adding 1 there, and then we just put a plus c there. Right? So the derivative of this will be that. Okay, but this one I solved by just recognizing that it fit that pattern, not the substitution. So let's practice using substitution so that when they get a little more complicated, which they will, we'll have the ability to use substitution to solve it. Okay, so what we want to do is obviously substitute. So u is a go-to favorite as the letter to use. So let's let u be my substitution. And now this is the hard part. We have to pick exactly the right thing to let u be in order for the substitution method to work. And as you might have guessed, we want to let it be equal to this. This becomes x squared plus 2x plus 5. So we're going to be able to replace all of this here with a u. So far we'll have that this is the integral of, and then we'll have a u there to replace this to the power of 7. Okay, but the thing is we have to replace all of it, right? You have to be careful. You can't just replace part of it. You got to replace all the x's, every single one, and also the dx. So what you have to do is think about finding the derivatives. Let's come back over here. So now if we take the derivative with respect to x of the u function on one side, and then the derivative with respect to x on the other side, which was x squared plus 2x plus 5. Then on the left-hand side, of course, I just have du dx equals to, and then here I can find the derivative. That's equal to 2x plus 2. Now I'm going to multiply both sides by that dx. We get that du equals to du over dx equals to 2x plus 2. So I'm going to multiply this side by dx, multiply this side by dx. These guys cancel. And what I have then is that du equals 2x plus 2 times dx. Well, and lucky for us, that's exactly what this is. So in our substitution, we're going to let this whole thing be the u, And it turns out that this whole thing, including the dx, is equal to du, right, as proved over here. So all of that gets converted into just the du. Good, so there we've completed our substitution. The entire thing has been rewritten as an equivalent integral involving the letter u, where u represents this function. Good, so now that's an easy one to integrate. That's just going to be equal to u to the power of 8. And then, of course, we adjust for that constant by multiplying by 1/8 plus a constant. And finally, we resubstitute the value of u to get our final answer of 1/8 times x squared plus 2x plus 5 plus a constant. So we get the exact same answer. This one matches what we got before. Right? So this one I got because I recognized this was an easy pattern. It fits that pattern. It's pattern 1 from above. But here, if you don't recognize that pattern, we use the substitution method. And as you'll see, the substitution method can help us solve some pretty complicated integrals. Okay, so here are the steps we want to follow when we want to do the substitution method. Number 1, select a substitution that appears to simplify the integrand. That, by far, is the hardest thing to do. Sometimes it's really, really challenging to think about what a proper substitution should be and why it would end up simplifying your equation. So in particular, try to select u so that du is a factor in the integrand, right? So pick a u such that its derivative is in the function that you're trying to integrate, the integrand. Okay, like I said, that could be tricky, just takes a little bit of practice. Number 2, express the integrand entirely in terms of u and du, completely eliminating the original variable and its differential. Okay, so that's a part where I think people often make a mistake. You can't just replace part of the function with u, you got to replace the entire thing. So that can get a little tricky. Again, a little bit of practice. 3, evaluate the new integral if possible. Hopefully, what you've done is taken a really complicated integral and managed to rewrite it into a new integral that's easier to solve, right? Otherwise, what's the point? Why would you take a really ugly integral and turn it into another really ugly integral that you can't solve, right? So hopefully, your choice of u results in a new integral that's easy to solve. And 4, express the antiderivative found in step 3 in terms of the original variable. So don't forget that the original question was probably not given in the letter u, so we gotta resubstitute u and go back to the original variable of the question asked. For example, okay, now let's look at this one. We have the integral of x to the 3rd power minus 5 raised to the 4th power times 3 times x to the 3rd power. So again, this is another straightforward, easy one. We can see that this, if we let this be u, its derivative is going to be right there. Okay? So that's what we're going to do. So inspired by that recognition, I'm going to let u equal to x cubed minus 5. Good. Now the derivative with respect to x, ddx of the u on one side, ddx of x cubed minus 5 on the other side. This becomes du dx equals to 3x squared minus 0. And then du equals to 3x squared times dx. Good. Okay, so then that right there, all of it, let me highlight it, all of this, including the dx, is my du. So I'm ready for my substitution. So I'm going to bring it over here. The integral of x to the 3rd power minus 5 raised to the 4th power times 3x squared dx. This part right in here is going to be u, so it's going to be u raised to the 4th power, whereas this entire thing is going to be my du, right? Including the 3, Be careful with the constants. The entire thing has to be exactly like that. So now this becomes a new integral, which will be u to the power of 4 du, and that's an easy one to solve. We know that that becomes u to the 5th power, and then we have to adjust for the constant, plus c. And now finally, rewrite your u back into your original variable, which is x to the 3rd power. So this becomes 1 over 5 x to the 3rd power minus 5 raised to the 5th power plus c. Okay, like always, you can check to make sure that you got the right answer. If you have the right answer, it must be true that when we take the derivative with respect to x of 1/5 x to the 3rd power minus 5 raised to the 5th power plus c, that the derivative of this is equal to that integrand right in there. And as we can see, that's exactly what's going to happen. The derivative of this is going to be equal to 1/5 times 5 x to the 3rd minus 5 raised to the 4th power times the derivative of the inside part, which is 3x squared, and then this 5 and 1/5 cancel. So we get exactly what we expected, x to the 3rd power minus 5 raised to the 4th power times 3x squared. Okay, now let's try working with this one. Find the integral of x to the 3rd minus 5 raised to the 4th power times x squared dx. So let's let u equal to x to the 3rd power minus 5. And so now if we take a derivative with respect to x, we get that dx of the u is equal to d dx of the x cubed minus 5, which gives me that du dx is equal to 3x squared minus 0, so 3x squared. And so now if we solve for du, we get that du equals to 3x squared dx. Okay, so almost there, except it's missing the 3. Okay, so we have to be careful. It has to be exactly the same for us to do a substitution. So I'm going to have to tweak it just a little bit. So I'm going to say that this is the integral I'm interested in solving. Minus 5 to the 4th power x squared dx. But I wish there was a 3 right there, right? If I put a 3 right in there, then this would be exactly the du that I'm interested in. So I'm just going to put it in there. This becomes x to the 3rd power minus 5 raised to the 4th power x squared dx. So I'm just going to introduce a 3 right in there, just so that it looks exactly like this du. Now you can't just go around introducing or multiplying by 3 unless you also balance it out. And so I'm going to balance it out by multiplying it by 1/3 as well. Right? The times 1/3 times 3, this 3 and this 1/3 cancel out there, they just become a 1, right? Or if you like, we can also think of it this way. I'm going to multiply by a new version of 1, which is 3 over 3. And then I'm going to bring that in there. And so 3, and then that reduces with that, right? So any way you like to think about it, I haven't changed my original function. I've just multiplied it by a clever version of 1. And 1 times anything doesn't really change the value. Good? Okay, and the reason we do that is because now this is my u exactly, and this is my du exactly, including the constant. Good, so now we can say that this is equal to 1/3 integral of u to the 4th power du. And we know that this one's easy. This is going to be equal to 1/3 u to the power of 5, and we got to adjust for that by multiplying by 1/5 plus a constant. So we're almost there, except we have to, again, resubstitute that u. So we get that this is going to be 1/15. U is equal to x to the third power minus 5, all of it raised to the power of 5, plus a constant. Okay, let's try this one now. So if we think about 4x to the third power as our function, or as our value u, its derivative would be equal to 12x to the second power. So it's something to do with x to the second power. So let's let u equal to 4x to the third power. And now if we take a derivative, ddx of u equals to ddx of 4x to the third power. So this becomes du dx equals to 12x to the second power, which means that du equals to 12x to the second power dx. And again, we're going to have to make a clever introduction of a constant. Good. So if you're wondering, well, how did I know right away to let u equal to that? Well, it just comes with a little bit of practice and just experience. Okay, so now let's come over here. This is the integral that I'm given, e to the 4x to the third dx. And I'm going to say, well, I'm just going to switch these two things around because I want them to be right next to each other just so that it looks nice. And I'll have e to the 4x cubed and then an x squared dx. Right, so all I did is switch these two things around. Everything's being multiplied, and I just made a little space there because I know I'm going to introduce this 12. So I want a 12 right there, and I balance it out with a 1 over 12. 1 over 12 times 12 equals a clever version of 1, and 1 times anything retains the same value. Okay, so now I can do my substitution. I'm going to let this part right up here be my u, and all of this over here is my du. So we end up with 1/12 integral of e to the u du. Good. And so now that's an easy integral to solve. That's going to be 1/12 e to the u. That's the integral of e to the u, plus some constant. And then finally, we just got to make sure we resubstitute the u back. And so the u was 4x to the third power, plus some constant. That'll be our answer. Okay, so now let's try this one. Integral of x times x plus 6 to the power of 8. Okay, so let's let u equal to x plus 6. Then if we take a derivative with respect to x of the u, we end up with du dx equals to, and the derivative of this is just going to be 1. So therefore we just end up with du equals to dx. Okay, so then let me put it over here. We have the integral of x and then x plus 6 raised to the 8th power and dx. And this is going to be my u. And this is just my du by itself. But we have a problem. What do we do about this guy? Okay, so don't ignore it. It's not correct to just somehow throw it in there and say that it's u to the 8th du. That's ugly, right? We need to rewrite everything in terms of u. You can't ignore it. We can't separate it. Another common mistake is that people decide maybe to put the x out here and then u du. That's not good. Or some other weird thing like x plus integral u 8u du. Right? So these are all wrong. Do not do any of that. That's not going to work. We can't ignore it. So what could we do with it? Well, in a case like this one, we got to come back over here to our substitution. We let u equal to x plus 6. So what we could do is say, well, if u equals to x plus 6, we can subtract minus 6 from this side, minus 6 from that side, and then conclude that u minus 6 must be equal to x. So we can again do a complete substitution. This x can be rewritten as u minus 6. And then we'll have something that's completely written in u. Okay, so let me rewrite all of that. I don't need any of these. Okay, so now we're ready to rewrite this. This is the integral of u minus 6 times u to the power of 8 times du. And this, at an initial glance, it looks like, well, you had something complicated and you did a substitution and you got to something complicated. True. Now, that happens sometimes. Sometimes you do a substitution and you go from something complicated to something even more complicated. And that's when you backtrack and maybe come back and reassess your choice for you. Maybe there was a better choice for you. But in this case, if you take a closer look, it actually is a lot easier to integrate, right? So here we had the binomial raised to the power of 8. We know that to expand that, that is really ugly, right? X plus 6 to the power of 8 is x plus 6 times x plus 6 times x plus 6 times x plus 6, right? 8 times. And to FOIL all of that, that's a nightmare. So we know that that's really, really hard. And that's why we want to avoid doing that. But here we were able to rewrite it, and now the power of 8 is just is an exponent to just the variable u, not a binomial. So this does make it easier. What we can do is distribute, and we end up with the integral of u to the 9th power minus 6u to the 8th power du. And now this can be separated as the integral of u to the 9th du minus 6 integral of u to the 8th du. You know, that's one of our properties of integrals. We can separate it like that whenever there's an addition or subtraction. So here this was the integral of that whole thing. Good. And so now this is easy. This is going to be equal to u to the power of 10, and then we multiply by 1/10, minus 6 times u to the power of 9, and then we multiply by 1/9, plus some constant. So we're almost there. Now we just have to make sure we come back and resubstitute my u, which was this x plus 6. So now our answer is going to be 1/10 x plus 6 to the power of 10 minus, and now the 6 and the 9 can reduce, 2/3. So we have minus 2/3 parentheses x plus 6 raised to the power of 9 plus some constant. Good, so that's our answer. Okay, so let me bring the original one down here so that I can have them. So this whole statement equaled this one, which equals that one all the way down. So what we have is that the integral of x plus 6 to the power of 8 dx is equal to exactly this. So let me make some space so we can check it. Okay, let's make sure that in fact this is true. If it's true, if it worked out, if this is really the answer, it must be true that the derivative of this equals to that, right? So let's check it. Check, is it true that the derivative with respect to x of the function 1/10 x plus 6 to the power of 10 minus 2/3 x plus 6 to the power of 9 plus some constant, is it true that all of that equals this integrand here? Okay, so starting with this derivative, we know that this is going to be 1/10 times 10 x plus 6 to the power of 9 times the derivative of the inside function, d dx of x plus 6, minus, and then this will be 2 over 3 times 9 x plus 6 to the power of 8 times the derivative of the inside function, thanks to the chain rule, x plus 6, and then plus the derivative with respect to x of c, which is a constant, so it'll be 0. Okay, so now we can reduce a bunch of things. Here, of course, the 10s will cancel, cancel. And 3 goes into 9 3 times, so we'll have a minus 6 there. And, of course, the derivative with respect to x of x plus 6, this is just going to be 1. And same as over here, this is just going to be 1. So let's see what we have. This is going to be x plus 6 to the power of 9 times 1 minus 6 x plus 6 to the power of 8. Good. Okay, so now we can factor out an x plus 6. Both of these terms have an x plus 6. Well, they have 8 of them, in fact. So we get x plus 6 to the power of 8 factored out. And then what we have here is one more copy of x plus 6 minus 6. And so now that becomes x plus 6 to the power of 8 times, and then the plus 6 minus 6 cancel to give me just x times x. So that's exactly what we expected right in here. We've confirmed that the derivative of this function, really does equal to that. Right? So as you can see, we started off with integrals that looked really, really obvious, but they can get kind of complicated. Right? It wouldn't have been intuitively obvious to say, oh, the derivative of this ugly thing is really just x times x plus 6 to the 8th. So we got to work the process and use the substitution method. Okay, a company finds that the marginal price P prime of x at a supply level of x bottles of baby shampoo per week is given by this formula. P prime x equals to 300 divided by 3x plus 25 squared. Find the price supply equation if the distributor of the shampoo is willing to supply 75 bottles each week at a price of $1.60 per bottle. Okay, so find P of x is what they're asking us to find. So I'll start over here. P of x is equal to the integral of P prime of x dx, which means that this is equal to the integral of this equation right here, 300 divided by 3x plus 25 parentheses squared dx. So let's use a substitution. So let's let u equal to 3x plus 25, which means that if I take the derivative with respect to x of both sides, I get du dx is equal to 3 so du equals to 3 dx. Okay, so now coming back up here to do my substitution. Okay, so I'm going to come back over here and say that this is equal to, scroll over here, the integral of, and then in the denominator I'll leave the 3x plus 25 squared dx, and then I want that 3, so I'm going to put a 3 here, I'll just put 1 there and make a little space here. Rewrite it as 3 dx. And well, I had 300, I just want the 3, so I'm just going to rewrite it as 100 out here, because 100 times 3 is the 300, so I just split up the constant that's there. And I did it this way because keeping an eye out on the fact that my du is 3 dx. So now I'm ready to substitute. This is my du, and this is my u. Okay, so that means that this is going to be equal to 100 integral of 1 over u squared du. And that's easy to integrate. That's the same thing as 100 integral of u to the minus 2 du, which gives me 100 u to the minus 1. Remember, the derivative of this is going to be to bring down the minus 1, subtract 1. That gets you to that minus 2. But we need to take care of that extra minus 1. So we have to throw that in there. The derivative of this is going to be equal to that. Good. Plus some constant. And now we simplify and substitute the value of u. So we get minus 100 divided by 3x plus 25 plus some constant is going to be my answer. Okay, so I kind of have the answer. This is p of x, except I'm not totally done because I don't know the value of c, and they did give me some boundary information to be able to figure out the value of c. Coming back over here. It's got kind of messy here, so let me maybe isolate this right here. This was kind of like a little bit of side work here. I probably should have put it on the side here. So the flow is this. P of x equals this. So P of x equals this, and it kind of goes this way, and I kind of got lost. Sorry. Be neater on your work. Okay, so we have an equation for P of x. So P of x then equals to negative 100 divided by 3x plus 25 plus some constant c. And now we get to use this other information. We're told that the distributor of the shampoo is willing to supply 75 bottles each week at a price of $1.60 per bottle. So we have that when x equals to 75, the price is $1.60. So we can use that information to figure out the value of c. So 1.6 must be equal to negative 100 divided by 3 times 75 plus 25 plus c. 3 times 75 is 225 plus 25 is 250. So 1.6 equals to negative 100 divided by 250 plus c. Here we can easily reduce an extra 0. That's 10 divided by 25. 1.6 equals to negative 10 divided by 25 plus c. And now 5 goes into 10 2 times. 5 goes into 10 twice. 5 goes into 25 5 times. So 2/5, 1.6 equals to negative 2/5 plus c. So 1.6 equals to negative 0.4 plus c, and that's what 2/5 is 0.4. And now if we add plus 0.4 to both sides, plus 0.4, we get to 2. So 2 equals to c. So c equals to 2. And now we have our full equation. P of x is then equal to negative 100 over 3x plus 25 plus 2. Okay, so that should be more than enough to attempt your homework. As usual, come to my office hours if you have any questions, problems, or issues.